a key reaction in our cycle for acid derivatives is knowing how acid derivatives are hydrolyzed back to the original carboxylic acid. So let's talk about this. I'm going to show the ester hydrolysis mechanism. For all these hydrolyses, no matter what acid derivative you have, you normally use water and sulfuric acid. We've encountered this reagent combination many times in this course, and when you mix these two things together, you form H3O+. So that's what I want you to think of. This is really H3O+. Anytime you treat something with acid, the first step is going to be protonation of whatever your starting material is. Now, as it turns out, when we're talking about carbonyl compounds, that carbonyl oxygen is where we're going to protonate. So that starts it off. Now, once we protonate a carbonyl, it goes from being a kind of a weak electrophile to becoming a strong electrophile. Now, that's good because we don't have any strong nucleophiles in our reaction. We got acid and water. But we do have a weak nucleophile, and that weak nucleophile is water. And now, by protonating our acid, we make it a strong enough electrophile for our water to attack. Whoops, let's go back on that. Now I'm going to make a note down here. Hopefully this won't be too long of a video. I'm going to make a note that the ultimate product of our reaction is going to be the carboxylic acid. So we have to get rid of our OR group and replace it with an OH. So keep in mind, we want to get rid of this OR group. And under acidic conditions, the way we're going to get rid of it is to protonate it. But there's a problem. Of course, there's a problem. We can't protonate this oxygen until we get rid of the charge over here. So we're going to have to do an intermediate step. We're going to have to find the best base we have available, which is going to be water. And we're going to deprotonate this oxygen that has a positive charge. Now that this oxygen over here is neutral, we can talk about putting a proton on the other oxygen. And of course, we're going to protonate with our available acid, which is H3O+. Now we protonate over here. Keep in mind our goal. We're trying to get rid of the OR group on our ester. So now we have our OR group protonated. It's ready to leave. Now, as it turns out, and I think this is important, not everybody agrees with me on this, this thing just doesn't leave. It's actually pushed out by one of our other two oxygens. You know, you can't quit, you're fired. Okay, so this neighboring oxygen helps eject that our OR containing group. And if you look at what we get, now we've gotten rid of our OR containing group, and we have this simply an OH attached to our carbonyl. Now our carbonyl isn't quite right. It's got a positive charge, and to finish this reaction, we just need to deprotonate the carbonyl, and we get our desired product, our parent carboxylic acid, which we can convert now to any other acid derivative we want. Just pull out thionyl chloride, make the acid chloride, and react it with some amine or some alcohol or alkoxide. So this is the acid catalyzed, because to do this we need acid around, hydrolysis of an ester. You can also do acid-catalyzed hydrolysis of amides. Both of them hydrolyze to give you back the original parent carboxylic acid.